Ready?
That's an easy to so it's in the middle of the day.
Okay, so moving on. Hello. They don't understand my ADD, do they? No, they don't understand my need for attention.
So last time around, we were able to prove that things converge. This time, we know what they converge to.
Nope. All right, ready, kids? Okay, so we're going to talk today about a specific kind of convergence called absolute convergence, and I'm going to introduce something called the ratio test and something called the root test. And because it's a short day because you have a quiz, I'm going to show you how to use the ratio and root test, which is kind of what's on your homework, and then we'll prove it next time so that you can start your homework if you want to be a good student and get ahead, because this is helpful. Okay, so the first thing is absolute convergence, and some of you noticed this last time. So we talked about the AST, and we had the sum from n equals 1 to infinity, negative 1 to the n over n. What did that do? This converged. And somebody observed that, wow, that's weird, because if I take out that negative 1 to the n, and I just make it 1 over n, what does that do? That diverges. So what operation could you apply to terms in the series on the left to get the terms on the right? Like, what thing could you do to these guys to get those guys? Take the absolute value. Does that make sense? If you take the absolute value, all the terms that are positive stay positive, right? All the terms that are negative become positive, right? That's what you did to get from left to right. And so series, okay, so that's kind of the idea what we're going to talk about to start today. So a series A sub n is called absolutely convergent. And that doesn't mean like absolutely, like certainly. It refers to its absolute values, as in if the sum of absolute values is convergent. So this thing that we just had up there, is that thing absolutely convergent? It's no, because does the sum of absolute values converge? No. Okay. What if I'd given you this guy, sum n equals 1 to infinity, negative 1 to the n over n squared? Does that thing by itself converge? Yes. If I absolute value the terms, does that converge? Yes, because it's a p series with p equal to 2. Okay? A series is called conditionally convergent if it is convergent, but once you take the absolute values, it's not convergent. So what this is saying is sum an converges, but sum of absolute values does not. So somehow taking away the positive negativity of it means all of a sudden that series doesn't converge anymore. What's an example of something that has that property? The series converges, but its absolute values don't. It's written on top. It wasn't a trick question. The example is the sum from n equals 1 to infinity, negative 1 to the n over n. That series converges, but when you take the absolute value, the stuff inside, no more convergence. And strange stuff happens. For things that are conditionally convergent, all of a sudden addition isn't commutative. You can't change the order anymore. When you have an infinite sum, that is. There's YouTube videos that try to do this, and they prove funny things like 0 equals 1/2. Like, you can look it up. It's weirdness, okay? All right. So determine whether following series are absolutely or conditionally convergent. Okay. So does this series as is converge? Yeah. Is it pretty obvious that this series converges by the alternating series test? That would not be a very hard AST to do, right? Your b sub n would equal 1 over n squared, right? Obviously, that goes to 0 as n goes to infinity, right? And b sub n's are obviously decreasing. Okay, now check the sum from n equals 1 to infinity of the absolute value of your terms. Oh, good question. How do A sub n and B sub n differ? Like with that AST notation, B sub n is just what part of the series? I think somebody said it, the positive part, right? Does that make sense?
What is AST again?
Oh, alternating series test.
Okay.
Sorry. Whereas A sub n includes the negative part. Does that make sense? Okay. So what happens if I absolute value -1 to a power? What do I get? 1 to a power, which is just 1. And if I absolute value n squared, well, n is positive, so n squared is its own absolute value, right? Okay. So what does this series do? It's a P series with P equal to 2. So the original series is what kind of conversion? Is it absolutely convergent or conditionally convergent? It's absolutely convergent. Okay. And then how about the next one? Does this series as is converge? With the -1 in there. Yeah, this series converges by the AST, alternating series test, and your B sub n would equal 1 over n. Remember, all that has to happen for the AST is the positive part of your series has to go to 0 as n goes to infinity, and those B sub n's have to be decreasing. Is that true for this guy? Yeah, it is true. Limit as n goes to infinity, 1 over n is equal to 0, check. And Bn plus 1, well, that's 1 over n plus 1, certainly less than 1 over n, right? So condition 2 also check. Okay. Now check the absolute values. So what's the absolute value of -1 to the n over n?
1 over n.
And the reason that you can say the absolute value of n is just n is because your n ranges from 1 to infinity, which means it's always positive. Does that make sense? If your n ranged from -infinity to infinity, then you couldn't say that, but that's never going to happen in this class. Okay. What does this thing do? Diverges. You can either say it's a P series with P equal 1. It also has a name. Do you remember its name? It's the harmonic series. Okay. So thus, the original series, is it absolutely convergent or conditionally convergent? Is conditionally convergent. Is conditionally convergent. Okay, is that all right? All right, now the question is how does absolute convergence just relate to plain old convergence? And it turns out that if you know your series is absolutely convergent, then it is convergent. Another way of saying that is absolute convergence. Have you guys seen this symbol that means implies? That just means implies. It's kind of like an equal to sign with an arrow on it. It's not a smiley face. My high school kids thought they were smiley faces. Absolute convergence implies convergence. Is it true the other direction? Okay, good, no. Does convergence imply absolute convergence? And the answer is no, right? Like the form we just had in part B, right? That series converges, but it does not converge absolutely. And to me, this should kind of make sense because if you take the terms and you absolute value them, they kind of like get bigger than the other thing, right? So it's kind of comparison test-ish, but we can't use the comparison test because we can't do comparison with negative stuff, right? So here's how you get around that. So the first thing you do, and this is just, you're not supposed to understand but not reproduce, observe that 0 is less than or equal to an plus the absolute value of an, which is less than or equal to 2 absolute values. Do you buy that? Because one of two things happens. Either your an was negative, in which case you have an, well, anyhow, yeah, if your an was negative, then what will an plus an's absolute value make? 0. And if an is positive, an plus its absolute value will make 2 times an or 2 times absolute value, no big diff, right? And I want to add one thing to start. So we're going to assume some an is absolutely convergent. Like, assume that happens. Okay. So do you agree that we know that the sum of absolute value of an converges? Because we assumed the series was absolutely convergent? Do you buy that? Then what can you say about the sum of 2 absolute value of a sub n's?
Really convergent.
It's just, well, so if this thing converged to like 10, twice it's going to converge to 20, right? So it's still convergent. Okay. And so this means that the sum of an plus absolute value an converges by what test? So these terms, the an plus an absolute value, they're less than 2 absolute value of an's, right? And we know that the sum of 2 absolute values of an converges. So if something is less than a convergent series, it converges by direct comparison test. Yep.
You abbreviate that to DCT?
Yes, if you want to call that DCT, that's okay. Okay. And then lastly, this is a little bit tricky, but here's the go. The sum of an is sum of an plus absolute value of an minus the sum of absolute value an. You can express it this way.
Well, that makes complete sense, actually.
That makes complete sense? Okay. And the thing is, you know that, anyhow, this converges and this converges, right? So then you can make this into but anyhow, when something is a difference of 2 convergent series, this implies that the sum of an converges. And this test doesn't really have a name, so when you use it, you should say something like, you know, absolutely convergent implies convergent. You should say something like that in your explanation. Okay. So in the interest of time, I think I'll do like example 2A and just skip B because 2B is pretty similar and you can look at the notes online. So, show these series are convergent. Why can't you apply the AST? What's wrong with this one? Yeah, the terms don't alternate anymore because sine of n doesn't flip-flop in a consistent -1, +1 pattern. And so the terms are not alternating. But the idea is it looks a lot like a p-series, doesn't it? Do you agree with that? Because you have like sine, which is, at most 1, right? Over n squared, so it's kind of p-series-ish, yes? So the technique to apply here will be to show this is absolutely convergent. And therefore convergent. Okay. And when you're trying something that's absolutely convergent, you look at the absolute values of the terms. Like that's what absolute convergence is. So what you're going to notice is that the absolute value of sine n over n squared is less than or equal to what? I think I missed an n there. Okay. 1 over n squared. So since I have this relationship going this direction, and if I absolute value get positive terms, what test do you think you're going to use? Direct comparison, yep. So since the sum of 1 over n squared converges, say p equal to 2, the sum from n equals 1 to infinity absolute value converges by, we'll say DCT for the direct comparison test. And then therefore the original series, sine n over n squared is absolutely convergent and therefore convergent. Absolute convergence is kind of like better than just plain old convergence, sort of more special. It's kind of like being a square is more special than being a rectangle. Okay, can you see how part B is almost the exact same? But what are you going to compare to in part B? Is it a p-series anymore? It's geometric series with r equals 1/2. Yeah. Okay. Great. So the reason that absolute convergence get thrown in this section is because the tests that you learn in this section are going to actually check for absolute convergence. Like by default, that's what they do. So this one we're going to skip. The ratio test. Suppose you have a series with non-zero terms. It's only requirement. Your series will converge absolutely if the limit as n goes to infinity of an plus 1 over an is less than 1. It will diverge if that limit is greater than 1. And it will be inconclusive, which this means the series could go either way. If that limit is 1. So is there anything that this reminds you like a little bit of from section 11.2? It's a little bit like the limit comparison test, sure, but the limit comparison test, your limit had to be any number c, right? As long as c was positive. What other thing had a breaking point at n equals 1?
P-series.
P-series did, so did geometric, didn't they? With geometric, when you had the sum a r to the n, as soon as your r was bigger than 1, your series diverged. When it was less than 1, it converged, right? The way you prove this is you do a comparison thing with a geometric series. So these things are kind of like geometric radii in some sense, sort of, okay? Oh, and then what does this an plus 1 over an mean? That means you take the n plus first term, it's like plug n plus 1 into your formula, divided by the nth term. And we're going to use this test a whole heck of a lot, and the biggest problem is that because we do that, students want to use it all the time. It doesn't work all the time. So if you ever have this happen, the limit comes out to be 1, you have to try a different test, like the AST, like the integral test, comparison test, stuff like that.
I'm trying to think of numbers where it's self plus 1 over itself would equal.
Well, let's do this, okay? Let's actually do this for a specific example. Okay, so tell me whether this converges or diverges. So I know a bit more than you guys. This is actually going to converge to e to the 5th. You'll learn how to do that in section 1110. So your calculator estimates e to the 5th power, okay? So, but that's an aside for fun for later. So let's sorry, I'm going to be consistent. So a sub n is the nth term of the series, which is 5 to the n over n factorial. We're going to imply the ratio test. And you can't abbreviate it RT because we have a root test as well, and that also will have initials RT. So, and what that test says is you find the limit as n goes to infinity of the absolute value of an plus 1 over an. Okay. Now what an plus 1 means is stick n plus 1 into that formula that I have written down for an. So if I stick n plus 1 into this, what do I get? 5 to the n plus 1 over n plus 1 parentheses factorial, right? Dividing by an is the same as multiplying by its reciprocal. Do you buy that? So I can say multiply by n factorial over 5 to the n. Is everyone okay with that? Okay. And now the question is how to simplify this. So with those 5 to a powers, I'll show you the long way once, and if you are comfortable skipping some steps, you can totally do so. 5 to the n plus 1 is the same thing as 5 to the n times 5, right? And then I have it times n factorial on the top. N plus 1 factorial begins with n plus 1, then 1 less than that is n, and then n minus 1, and it goes all the way down, right? So n plus 1 factorial is n plus 1 times n minus 1, blah, 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 blah. That thing really is n factorial. And then a whole bunch of stuff cancels. Like what? 5 to the n and the n factorial. And do I technically need those absolute value bars anymore? No, you could just absolute value everything, and then your n's are positive, so they can just, they absolute themselves. So that limit is equal to 0. And okay, our series will converge if this limit, converge absolutely, if this limit is less than 1. So is this limit less than 1? Yeah. So thus, the series converges absolutely. A big hint that you're going to use this test is that you see stuff to powers or you see factorials. This test works really well for stuff like that. You could check that this is actually e to the 5th by plugging it in your calculator, and cool. Okay, this guy. So an is negative 1 to the n squared over 2 to the n. Okay, so find the limit. N goes to infinity. An plus 1 over an. So when you input n plus 1, what do you get? Negative 1 to the n plus 1. And?
Plus 1 all squared. squared.
n plus 1 all squared, spectacular, over 2 to the n plus 1, yep. And then divided by an, i.e. multiplied by its reciprocal, you have 2 to the n over negative 1 to the n and n squared, right? Okay, I really am somewhat lazy at times. And negative 1 to the n plus 1 and negative 1 to the n, what happens to them when you absolute value them? Becomes positive 1, right? So they just go away. Does that make sense? Don't worry about them. In the numerator, we have this n plus 1 squared, which is n squared plus 2n plus 1. What happens with the 2 to the n plus 1 and the 2 to the n? Cancels out, and you're left with a 2, and it's in the denominator, right? Yep. The first term, i.e. the denominator. Yep, exactly. Is there anything else left from the other denominator?
N squared.
N squared. Great. And don't show me your work. Tell me where that limit goes. Limit goes to 1/2, which is less than 1. So the series converges absolutely. I want to say one thing and then you can ask your question, okay? Why is this wrong? So AN converges. Why is that incorrect? What did the person who did that forget? The sum symbol. If you don't put the sum symbol, it's a sequence, right? So don't forget to put your sums. You can do that if you put your sum symbol. Just don't forget the sum symbol. Okay? And they probably should also index it 1 to infinity, like just to be extra careful. Okay? I'd love to see nobody make that mistake because I'm super annoyed by it. You had a question.
Yeah, so when you're doing the limit comparison test, it's completely different. Does the A sub n always have to be smaller than B sub n for the limit comparison test? Or can you just arbitrarily say A sub n?
No, with the limit comparison test, you just pick something that you know what the series does.
Okay.
So it's similar in the fact that it's a ratio, but that's where the similarity ends, really. That's the only similarity, is that it's a ratio. Because with that test, if your result that you get is some positive number, even like 10, what your series does depends on the thing you're comparing it to. So it is definitely different. It also only works for things with positive terms, whereas this one doesn't have positive terms. The next test, which we'll do next time, is called the root test.
That's
And
why the negative cancel, because the negative 1 to the n cancels, so you have negative 1 to the 1, isn't that negative?
it is, but you have absolute value, because you have absolute values.
Value bars, okay.
Yep, so the absolute value bars mean that then absolute values to positive 1. Yep, exactly. No, that's fine. But the negatives, they just go away. You absolute value them and they're just gone. Okay. So, you guys ready? Ish?
Are we gonna do the fruits now?
We're gonna do this example 4 first. So, example 4 uses something called the root test. And the root test is quite similar to the ratio test in the way that the boundary values are the same. Does that kind of make sense? You see what I'm saying? Like with the ratio test, if you did the ratio test and you got that the limit was less than 1, then the series converged absolutely, right? When that limit was bigger than 1, the series diverged. And if the limit was equal to 1, well, then you just don't know, pick a different test. And we'll talk about which kinds of things this test won't work for. But the root test does the same thing, except for you take the nth root of something. So if you take, like, the third root of x cubed, what happens to the power? Third root x cubed power goes away, right? Fifth root x fifth power goes away, right? Nth root of stuff to the n, the root goes away. So this is a really useful test when you see stuff like the things in example 4, where both the numerator and denominator are raised to like an n power.
So wait, could you change that to be like e over n to the...
Kind of. So let's just let a sub n equal e to the 3n over n to the n. We're going to apply the root test. That's from last time, so you should have one already. take the limit as n goes to infinity, nth root, absolute value of an.
But how do you take the infinite root or something? Or is it supposed to drop off?
It'll drop off, just wait. So nth root, absolute value, e to the 3n over n to the n.
Okay, so this rule, you use it when L'Hopital's rule doesn't work.
Well, L'Hopital's rule applies to limits of sequences, but we have a series.
Oh.
Do you see what I'm saying? Like, it's not a list of numbers anymore, it's a sum of the list of numbers, so you can't use L'Hopital's rule. But with this thing, the ratio test, if you tried to do it, would result in a limit that was hard to find. That's all. But, so first of all, one thing, do the absolute value bars matter?
No.
No, they can just be go bye-bye because everything's positive. So limit n goes to infinity, nth root. Can I write this as e cubed over n all to the nth power? Does that make sense?
Wait, why doesn't the n just cancel out with its own n?
Because that's like n to the n power, so it's like 2 to the second, 3 to the third, 4 to the fourth.
Kill the kitten.
Yeah, you killed a kitten. Yep. But something does cancel. What does this nth root do to that overarching nth power? That cancels it out. And we now have the limit as n goes to infinity of e cubed over n, right?
So a number less than 1?
Yeah, well, actually, even better. What number does that actually limit to?
0?
0, exactly. You've got a constant over n.
I was told in recitation that you couldn't say that you had to say it was like, if it was like 1 plus something over infinity, then you had to say it was a number slightly bigger than 1.
1 plus...
Like e cubed over infinity. Then you had to say, no, not the whole thing over infinity, just the e cubed.
like this.
Wouldn't that go to 1?
Yeah, that approach
Well,
1.
I said that, and then he was like, no, that's not what happened. It goes to like 1.000 something, and I'm like,
Oh, yeah, technically.
Well, yeah, anyhow, okay. So anyhow, this limit goes to 0, so as a result, what happens to the series? And even better, it converges absolutely. Which means both that the series converges and if you were to take the absolute value of the terms in the series, they converge too. In this series, taking the absolute value doesn't change anything because the terms are all positive.
do we have to claim that it converges because it converges absolutely? or
No,
is
you
that-
can just say it converges absolutely, and I'm just gonna hope that you know that that means converges as well. Okay. This guy, so a hint that you're going to use this test is that you see something to the nth power. That is the biggest hint. So in this one, we'll let an equal negative 2n over n plus 1 to the 5n.
Now the absolute value matters.
Now the absolute value bar matters, exactly. Nth root an.
Does it just get rid of the negative there?
It really does. I mean, so your book, I don't think we're going to be super picky about how you do this, but I do have students who mess it up, so I think we should be a little bit careful. It's okay to change the order of these operations. Well, actually, no, what we can do now is, I got it, okay. So, first of all, the nth root does what to the power of 5n? Turns it into just 5. Does that make sense? Okay, so this is the limit as n goes to infinity. Absolute value, negative 2n over n plus 1 to the 5th. Okay. Now, what happens to the stuff in, remember how limits can go inside of continuous functions? The absolute value is a continuous function, right?
So is the fifth.
So the limit can, so is the fifth. So the limit can go inside of that thing. And this is the technical step that you're totally okay. I'm okay with you skipping this in the future. Negative 2n over n plus 1 to the 5th. So where does that stuff inside the absolute value bars go?
Negative 2.
Negative 2. And then it gets raised to the 5th power. And absolute value, so it's going to be 32. you don't have to show this whole moving the limit inside step. But the reason that works is that you can move limits inside of continuous function. We did that with e's, right?
Yes.
We did it with natural logs, right? Okay, and so 30,
E is a continuous function though. By itself, it's just a number, right?
but it's e to the x, right?
Oh, okay.
That's a continuous function. How does 32 relate to 1? It's great, it's a lot bigger, right? So the series, relatively, yeah, I mean, but since, yeah, anyhow, the series diverges. I have a lot of students in the past who, I don't know if it's because they're in a distance class and they don't like actually listen to me talk in the videos, they will say that this value, that limit equals minus 32, and then they conclude the series converges.
Because it's less than.
Because it's less than 1. So you should never, ever, 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 ever get a negative number out of this.
Unless
Do
you
you see
move
what?
the negative sign out of
No,
it, so that-
never. You limit something you've taken the absolute value of, it always is positive. If you
No,
apply the
so-
ratio and root test, you get a positive result.
Here's an
Period.
error you can make.
Period. Done.
Did
Okay.
they forget the absolute value bars?
They just forgot to apply them.
Okay.
That was and it happened with like alarming frequency. I do not know what was wrong with people. Okay, I don't understand.
You screw up absolute value.
Okay. So here's the proof.
No, we deliberately put that there.
I deliberately put that there. So we're just going to prove the ratio test. All right? This involves comparison to a geometric series. So that's the basic idea. Compare to a geometric. So first thing we do, write a little bit small here. Assume the limit as n goes to infinity, an plus 1 over an is equal to some number L that's less than 1.
Probably should just make calculator.
Okay, does that make sense that you can do that? We're just kind of proving the first case, which is the hardest of the cases to prove. Okay. Now, if your limit is some number that's less than 1, we're going to be able to choose some r such that this L is less than r, which is less than 1. Does that make sense that that's theoretically possible? Like if this L was 0.99, you could pick a number that's like a teensy bit bigger than it, but still less than 1? Okay. Now, as the absolute value of a sub n plus 1 over a sub n goes to L, eventually that ratio, an plus 1 over an, is less than r for all little n bigger than or equal to some capital N. Does that make sense?
What's the capital N?
A capital N is like a number in your sequence. So you have this list of an plus 1 over an's. They're approaching this number L. And if you go far enough out, eventually that ratio is less than that r number. So it's like saying that once I go past like 100, then from 101 on, I'm less than that ratio is less than that r number.
Okay.
By that? Okay. And so then what we have is that the absolute value of an plus 1 is less than r times the absolute value of an. Do you buy that?
That's R multiplied by the absolute value of A.
Yep, so all I did was took this ratio here, right? And I multiplied the absolute value of an onto that side.
Okay.
Does that make sense? And then and because I know that's a positive thing, the sign doesn't flip, right?
And where's the big N come from?
This big N just says that eventually, that's where the whole eventually thing happens.
Okay.
Eventually, this happens. Like you have this limit L, I don't know why I just made it 4 because it's like less than 1. Have this limit L, you have some number R that's close to but a bit, wait, no, RR is, here's our 1. That's the sort of boundary point. And then you have some limit L and up here is your R.
Big eraser.
I actually think I selected the smaller one, but I don't think it's small enough anyhow. But I appreciate the warning. And what that means is once you go past this N, those things just, they stay less than R, that's all.
Okay.
Whereas before it, they could have been like up here. Because the limit going to place means eventually it settles down and gets close to that number.
Right.
So eventually they're settling down and getting close to L. So that's what this is just saying, like, this is the point at which they settle.
You need to keep those
Which would be
domains-
different for different sequences.
You need to keep those domains in mind.
Not really. You just know that it happens at some point, and you can just give it a name and it can change. And so then what we have is that A sub capital N plus 1 is less than R A sub capital N. Because that's true for all little n's bigger than that n. Does that make sense? Like n is bigger, yeah, capital N is bigger than or equal to itself, right? So what if I wanted to talk about A sub capital N plus 2? That'd be less than R times the absolute value of A sub what?
N plus 1.
Capital N plus 1. Do you buy that? So what that's using is this relationship with n equal to n plus 1. Is that okay? And here's where you use, and don't you know that this thing is less than R times absolute value of A sub capital N? Do you see that? So I have right here, I have A sub capital N plus 1 is less than R times absolute value of A sub N, right? So this R times A sub N absolute value is bigger than the absolute value of A sub N plus 1. So I can say, well, if I replace this A sub N plus 1 with another R and an A sub N, my thing got bigger, right? And that's the same thing as R squared absolute value A sub N. We'll do one more. How about A sub capital N plus 3? That's less than R times the absolute value of A sub N plus what? 2? And do you know something that A sub N plus 2 is less than, or something that's bigger than it?
R squared A sub n.
Didn't I just say this? Right? A sub N plus 2 is less than that thing, right? So this is less than, that R is still there, R squared absolute value A sub N, which is R cubed absolute value A sub capital N.
Couldn't have been a less than. No, it does.
Well, the less than is here, but in that case it's equal to. Do you see that there's a pretty obvious pattern here? What is the absolute value of A sub N capital N plus 4 going to be less than? R to the 4th absolute value A sub capital N, right? Okay.
But R is a number less than 1, so shouldn't that be continuously decreasing?
That's the kicker here. That's how it's comparison to the geometric series, actually. So we just take a look at this so I say it right. Okay. So do you buy that the series sum from n equals 1 to infinity, absolute value of A sub n, R to the k converges?
Yeah, because
So
if the
why?
R term keeps going down, and it's still bigger than whatever the A sub n term.
The R term isn't, the R term's actually constant, but what do you know about it?
No, I mean whatever you're saying with the expression with R in it,
Yeah. But
that's
that-
continuously decreasing.
When you have an R that's below 1, right?
Yeah.
And that's the kicker, is that this R is below 1, right? So therefore, that series is convergent. What kind of series is it?
Geometric.
It's geometric. Okay, and this like is the sum of a sub n times r to the first, right? A sub n, r to the second, etc. So what that tells us is that this thing, absolute value a n plus 1 plus absolute value a n plus 2, that's what all this like sort of stuff was here. Why? Etc. Also converges. And let me explain that a little bit better. So the absolute value of a n plus 1 plus absolute value of a n plus 2 plus junk. That's like adding up all these things on the left side of these inequalities. That's a less than or equal to this geometric sum we just stated converges, right? Okay, does that make sense? Because we have a n plus 1 is less than that first term, and a sub n plus 2 is less than the second term, etc., right? And what this thing here is, that's a sum from n equals capital N plus 1 to infinity, absolute value of just your a sub n's. Does that make sense? And so this thing converges technically by comparison, right? And here's the last thing you have to conclude. Does this mean that the sum from n equals, we'll say 1 to infinity, of absolute value of a sub n also converges? How come?
Because it's less than whatever capital N is.
Not necessarily. What this first thing says with the capital N plus 1 means you start at like, I don't know, 101 and go to infinity, right?
No, so
Will adding the first 100 things back in change the fact that the series converges?
No, just make it 100 things.
It'll just make it whatever that sum is bigger, right? But the point is, adding in a finite number of things will not change convergence or divergence. So, and if your series of absolute values converges, that means that your regular old series is absolutely convergent, right? The limit comparison test proof was a little bit like this too, wasn't it? Like you assumed you went past some sort of point, and then after that point you could make a comparison of some sorts. You're not going to have to prove this on your own, and your book has the other cases, so I'm just going to skip them and move on to showing you some tests. The whole part about this test being inconclusive at a certain point just means that if you get that result, it's not consistently a convergent series or a divergent series. There are examples of it going either way. So when you get a result that the limit is 1, you just pick a different test and try a different test. Or you made a mistake, okay? But one of the two. Okay. So the ratio test and the root test work really well for things that have powers and things that have factorials. So when you're looking to apply these tests, look for powers and look for factorials. If you see factorials, it's almost invariably the ratio test that you apply. If you have powers only, then the root test is better. Do you know what I mean by that? Like in example 4, we had e to the 3n power over n to the n. There were only powers, no factorials, right? Or we had negative 2n over n plus 1 to the 5n, right? Only powers, no factorials. Okay, so the root test is really, really, really helpful when you have only powers. But if you have factorial, the ratio test is the one to use. So check the limit of the ratio as an plus 1 over an. What that proof kind of said is that series like this, that fit this form, are kind of eventually sort of like geometric. And so they follow the same sort of convergence rules as geometric. This kind of finds there are. And be very careful when you input n plus 1. Like put the n plus 1 in parentheses for n. So we'll have a sub n is negative 3 to the n over 2n plus 1 factorial. When you input n plus 1 for n, what do you get in the numerator?
Negative 3 to the n plus 1.
Negative 3 to the n plus 1, right? In the denominator, you have 2 parentheses n plus 1, and then factorial. Do you see what I'm saying? Which actually is going to be 2n plus 3. And then dividing by an is the same as multiplying by its reciprocal, which is, someone tell me because I'm going to drink some water.
2n plus 1 factorial over negative 3 to the n.
Good. Do you guys agree with that? Okay. Negative 3 to the n. Yeah, I understood what you mean.
I actually did that to myself.
Now, can you split up that negative 3 to the n plus 1 and cancel it?
Yes, you can. Do you guys agree with that as well? That negative 3 to the n plus 1 is negative 3 to the n times negative 3, right? So we can just cancel that to negative 3. Gesundheit. We have 2n plus 1 factorial. And then the bottom we have 2n plus 3 factorial. Is that all right? Is that okay, the whole canceling thing? I could also drop the absolute value bars if I just find the absolute value of that negative 3, couldn't I? It's the only thing that's negative, so that's 3. 2n, okay, what's the small eraser selected? 2n plus 1 factorial. Okay. When you're canceling factorials, start with the bigger one, and that should cancel out part of the smaller one. The question is just how much. Or the smaller one should cancel out part of it. Sorry, I said that incorrectly. So think 2n plus 3 factorial. It begins at 2n plus 3, right? And then it decreases by 1s, right, forever. So 2n plus 3 is the first term. What's 1 less than that? 2n plus 2. And then 1 less than that is 2n plus 1, and everybody down, which means it's factorial. Notice how there were 2 terms there. There was a question on your first quiz, the one, quiz 5, not quiz 6, that had you find a limit of a factorial thing. That should simplify down quite nicely. So check the solutions and try to do that because it's a similar idea. That's why we put it there. So we have the limit as n goes to infinity. 3 over 2n plus 3 times 2n plus 2. Okay. And when you do these limits, I'm going to not only check that you get an answer and make a conclusion, but you've got the right work because you can get lucky and get the right answer. Does that make sense? You still get points for no and stuff, but I want you to be both right. And where does this limit go? 0, which is less than 1. So the series does what? Converges absolutely.
There was so much work there, you kind of blocked out my ability to work on the next problem.
The next problem is not nearly as long. Is that all right? Okay. How about this guy? Okay, first let's write the an as n over e to the n. Make sense? You may have seen this problem. I don't know if I assigned it or not because I just can't remember. But you could do this with the integral test as well. It's just a lot harder. It's much easier to use the ratio test.
Why not the root test?
Good question. Why not the root test? They're not both raised to a power.
N's raised to the first power. And
The root test is really useful when they're both raised to the nth power.
Okay.
That really is the kicker. Otherwise, you don't want to use it.
Okay.
Yep. So limit n goes to infinity. It was a good point, though. an plus 1 over an. Okay, so inputting n plus 1, what do I get? Great. And then dividing by an, same as multiplying by an's reciprocal, which is e to the n over n. Spectacular.
So it really is not gonna take me this much work. But there's some.
Almost choked my water there. There's some canceling that will happen. So yeah, do any of the n's cancel?
No.
No, don't kill any kittens, please. N plus 1, n. How about any of the e's? A lot of them cancel, but there's one left, and where is it? In the bottom. And why could I drop those absolute value bars?
No, that's not.
Everybody's positive. Okay, good. So where does this limit go? 1 over e. And you know that that equals exactly to know that this is less than 1, right? Because e is about 2. 2.71. Yep, it's closer to 3 actually. Therefore, the series converges absolutely.
I feel like this is easier to use than the limit test.
Limit comparison test?
Yeah,
That was not so bad either.
I don't even remember it.
Yeah, well, that's the bare thing about all the tests. Oh, just so you guys know, on Friday, which is tomorrow, right? That lesson is like a summary of all the tests, to like give you a chance to breathe. As in, like, we'll go through all of them, how to use them again, sort of a summary of all
Is
of them.
that because the exams come up?
Nope, because after that it kind of shifts a little bit, talk about how to use, what we're going to use these series for. So it sort of is like a sort of summary point, and then we'll talk about applications of them next. Huh? You can find integrals with these things, and you can approximate numbers with these things. Like, I think I told you on a different problem that this thing was equal to e to the something. And you were like, what? And so we'll teach you how I could tell that.
Is that how they found the experimental?
It's how your calculator approximates e. Like you type e to the 5th in your calculator and push go, or enter, right, which is what go is. And that's what it does. It uses this series thing to approximate it.
Is this how we discovered it experimentally?
I don't know. That's a good question. I'm not sure. Okay, so for this one, because both things are raised to the n power, use the root test.
I'm pretty sure that's not the only way to find e. I think e just naturally pops up in a lot of places.
I think that's, yeah, just like there's not only one way to find pi. So,
And now they're both n's.
yep, exactly. Absolute value an. Negative 5 over n, all to the nth. Anyhow, what happens to that nth power? It disappears. So limit n goes to infinity. Can I just make it 5 over n? Because like I could absolute value it and stuff. I could absolute value the negative 5 over n. I shouldn't say it if you guys can't say it. So that limit equals 0, which is less than 1.
No, do we have to write the less than 1 bit?
No. If you just tell me the series converges absolutely after you find that the limit is 0, I kind of believe that you know where the boundary is. Does that make sense? I'll be checking if you find the limit correctly and do you make the right conclusion.
So we have to say the absolute V all the time.
I think unless my directions say so, you could just say converges. Because if the directions, because the thing that can be hard about this would be showing a series didn't converge absolutely. Does that make sense? Like if you show, like you'd have to use like the limit comparison test, or you'd have to use something else, and it just gets kind of complicated. So if the direction is just, you can just say converges, but it wouldn't hurt to remind yourself that this is absolute convergence, just to know. But I won't dock you if you don't say it. Thanks.
How much, like, it's really important that we label AFN equals,
I don't think so. Some people will be really picky about that, but I don't really care. Some people will be picky about it because you didn't define what your AN is. I think it's just being sort of unnecessarily harsh.
Website makes you for everyone.
Does it? Well, it makes it easy if you do something, right? Because it's like, does the series converge or diverge? You can guess and check. I mean, right? So,
I love those ones. It's like you get 5 chances and 2 answers.
Yeah. I'm afraid I didn't try very hard, so you better get WebAssign right for this lesson, guys. Like, if you don't, you're not trying. And I judge you.
No, they do ask you what the limits are on this one, so
They do, yes. You have to do a little bit of work, yeah.
Now, if you get a wrong answer and then you get the same wrong answer again, does that count as 2 tries?
If you put it in twice, yes. If it tells you it's wrong the first time, it's not going to be right the second. Then you send me a message and you say, help.
You know, I'm just wondering, so I do a multiple part problem and I'm trying to figure out one of the parts, but the other part is incorrect and I keep saying submit answer. Does the other one count?
No, I don't think that. I think if you don't change it, it wouldn't count that again.
Okay.
If it's like, you change it just to a different form though, it will count it. So if you like do 1/4.
So if you leave it alone.
0.25, it'll count you wrong again.
Okay.
Okay.
All right, so when we input n plus 1, what do we get? Shh. Okay, tell me what you get for this. When you put input n plus 1 in for the n's, you get 10 to the n plus 1. Okay, what does that n plus 1 become? n plus 1 plus 1, which is n plus
2.
2.
I just didn't
Lovely.
want to say that because I could have been wrong.
4 to the 2 times, I'll do this one more slowly, 2 times n plus 1 plus 1. Does that make sense? Okay. And then times n plus 1, 4 to the 2n plus 1 over 10 to the n.
This one's not nice.
It's a little bit ugly, yes, I agree. But I think I promise to not only do easy problems in class, right? Because don't you hate it when teachers do that?
And then you
They do
get
the easy
hard-
ones in class and give you the hard ones on homework
Or on the test.
or on the test. Yeah, oh my goodness.
I'd have that.
N plus 2. So that becomes 4 to the 2n plus how many? 3. And of course, if you can get to that faster than I did, you're totally welcome to do that as long as you actually get there accurately. Okay. So, I don't really need those absolute value bars anymore, do I? Nothing is negative, right?
Yeah.
No, just nothing is negative. You have stuff to powers and your ends are always positive, so you're good to go. With the tens, what cancels? So what are you left with a 10 in the top? Great. Also an n plus 1. Okay, how about this 4 to the 2n plus 1 and 4 to the 2n plus 3?
Becomes 16 on the bottom.
It becomes 16 on the bottom. Do you guys agree with that? Do you see why? Because really it's 4 to the 2n times 4 over 4 to the 2n times 4 cubed if you like separate it out, right? Which cancels to 1 over 4 squared or 1 over 16. Also, didn't you learn in some alleged Algebra 1 class that when you're dividing, exponents subtract? So if you do 4 to the 2n plus 1 minus parenthesis 2n plus 3, you get 4 to the negative second, don't you? So that rule still applies.
I didn't learn that till Algebra 2.
That's weird. But anyhow, so what does this limit equal? Or reducing to lowest terms? 5 over 8, which is less than or bigger than 1? Less than 1, so this converges.
Excuse me.
Yes,
Could you show me how you did the 4 times 2 to the 1 and plus 1?
yes I can. Okay, so the work for 4 to the 2n plus 1 over 4 to the 2n plus 3. That's what you'd like to see, right?
No, I mean, how is that 2 times the quantity n plus 1? Because if you factor out the 2, wouldn't it be 1/2?
How is that? So your question is like, how is this?
Equal to 4 times 2n plus 1.
Oh, because first you take out a 1, and then you'd factor out a 2. So the plus 3 would become plus 2, and then you'd pull out the 2, and you'd get 2n plus 1 plus 1.
I'm not sure if I just processed that. So
Yeah.
you're saying how does this become this?
No, how is that equal to 4 to the power 2n plus 1?
How is this equal to 4 to the 2n plus 1?
How is 4 to to the power 2 times the quantity n plus 1.
There's no quantity. There's no parentheses there.
But there's parentheses on the bottom one.
Yeah, there's parentheses there,
Yeah.
but the 2 distributes only to the n, only to the 1, not to this one.
But how's that equal to 4 to the power 2 n plus, over there? Because in the beginning, when they first had the problem, you
Yes.
just changed it.
Well, because the ratio test, what you're supposed to do is input n plus 1.
But I mean, okay.
I think you just need to ask me after class, okay? Because I'm just not understanding what you're trying to get at. Like, I believe that I could clear it up, but I just don't know what you're asking. It just can't make sense of it.
Okay.
But what this term does is you input n plus 1.
Yeah, I understand.
Yeah, okay, understand that. And your problem is it with this term or with this term?
Oh, you're setting n equal to n plus 1. Okay,
Yeah.
never mind. Okay.
Yeah, okay, yeah, you replace n by n plus 1.
Yeah.
Yeah.
I thought you were like factoring out the 2.
No, I was not. No, you replace n by n plus 1.
Okay.
Exactly, sorry. Yep. That's kind of, it's just like, it's kind of like a function. Like what it means is you plug that value in for, yep, exactly. But it's tricky because you replace it with like a variation of the same letter, which is a little bit weird. Yes?
Could you use the root test if you, no?
No, when you do the root test, you end up with like an nth root of this factor.
But since it multiplies by the 4 to the 2 n plus 1, if you pull out.
Also, the root there doesn't work out so well. You can try, so try it. It's not going to work nicely. So you're going to end up with like nth root of something weird, and then you have to work out what that is, and that's not obvious. So the root test is kind of specialized, and honestly, some books don't even teach it. Like I think I took calculus 2 and didn't learn it because it's sort of so specific to one very small situation, which is both things raised to the n power or both things raised to like the 5n power. Other than that, you don't really use it. Yes?
Is there any situation where the root test applies but the ratio test doesn't?
Any situation where the root test applies, the ratio test could apply as well. It's just the limit you get might be hard to find. So, and that's the problem. You might get those limits where you have to use like natural logs to find them. Remember those where you had to natural log both sides? That's where the root test is good.
That's what I meant.
Okay, let's try one of these. Did you have a question?
Other than situations where the ratio is exactly equal to 1, will the ratio test always work?
Yeah, I mean, if you can work out where the ratio is not 1, yeah, it'll always work. Yeah, but when the situation, and there's also, it's easy to predict when the ratio is going to be 1, and I can tell you I got an example of that coming up.
Awesome.
Okay, sweet. So this one, because you have something raised to the n, and that's it, root test. So limit n goes to infinity, nth root, absolute value an. Arctan of n, all of the nth power.
Can we move the n outside the absolute value?
Yeah, and really what you're going to get here is the limit as n goes to infinity of arctangent of n, right? Because you only care about positive n's, so arctan you know, or you should know, because I keep trying to make you know this, looks like this, right? It's bounded at negative pi halves and pi halves. And so as n goes to infinity, where does arctan go? Pi halves, which is bigger than 1. Exactly. So can you see this is really kind of like a geometric series? You have something that's kind of like pi halves raised to the n power. So your r is kind of like pi halves, which is bigger than 1. It's just not exactly pi halves, right? Okay. So the series does what? Diverges. Yay. Okay.
And the next one, there should be some canceling in there.
The next one will have some canceling in there, yeah.
But maybe before you even.
So what test do we do?
Root.
Root test again?
But before you even did that part.
No, there's no canceling. I mean, ln of n and n are not, and like 1 over n are not equal. One is the derivative of the other, but that doesn't make them equal.
No, I meant like by raising the n on the bottom to the power of n, that natural law.
Oh, no, I see what you're saying, but no, and I can tell you why. after class. I think what you're trying to say, how is ln of n cubed different than ln of n, the quantity cubed? And one of those the power can pull down, and one of those it cannot.
And this is the second one.
The second one, the power does not pull down. It's this first one that it does. And you could plug in E and prove to yourself pretty quickly that that actually is the one that works, with a test point, for example. Absolute value, ln n over n, all to the, whatever, it's all to the nth power somehow. Ln n over n. So at this stage, I don't really care if you drop the absolute value bars because the natural log function looks roughly like this. What's this 1 point right there? It's point, x is 1, y is 0, right? And really your series went from 2 on, right? So anyway, who cares prior to that? So this is the limit as n goes to infinity of ln n over n. What rule can you use to find that limit? And don't change them to x's, I don't care. 1
Just
over
use
n,
dn.
yeah, 1 over n over 1, which is equal to 0, which is less than 1. So therefore this series, series converges. Absolutely, actually.
I never understood why you had to change to x in the first place, because dn.
Oh, I know, it's so silly, right? I mean, it's somebody being notationally picky, and I think there probably is a reasonable reason. I just,
Why you wouldn't take the derivative in respect to n.
they're just being notationally fussy. Okay, so here's my warning. If the ratio test or root test fails, you have to apply a different test to determine convergence or divergence. And one time that the ratio and root test will often fail is if you have something that's like a p-series-ish. And by the ish, I mean p-series technically have positive terms, right? Because that was the integral test. But even things that are polynomials, basically, this will fail, or ratios of polynomials. So let's just try to apply the ratio test to this, and I'll just show you that what's going to happen is an inconclusive result. And we'll talk about what other tests to apply. What test would you apply to prove that this series converges?
Integral.
Alternating series test.
Oh, yeah.
Why is the integral not okay?
Because there's a negative 1 right
Because there's negative 1 right there, exactly. Okay, awesome. But let's try the ratio test and look and see what happens. And students try really hard to always use this test, and believe me, on your actual test, we'll put some stuff on there for which it doesn't work. So like you have to be able to recognize, yeah, I shouldn't use that test now. So negative 1, n plus 1 cubed plus 1 times n cubed plus 1 over negative 1 to the n.
So this whole thing we're doing right now would be a complete waste of time on the test.
Yes, exactly. So in the future, don't do this. I just want to do it to show you what happens. Like you're going to get 1. Do the negative 1s matter? They just absolute value away, so kiss them goodbye. In the numerator, we have n cubed plus 1. In the denominator, if you do n plus 1 multiplied by itself 3 times, or if your Algebra 2 teacher taught you Pascal's triangle, you 2, you 3, I know you learned this, you end up with n cubed plus 3n squared plus 3n plus 2.
There's reasons.
That's what you do. Well, you do n plus 1 times n plus 1 times n plus 1, and then plus the other one. And you multiply those together, take your answer, multiply in this one, right? It just takes some time. I'm just being lazy. You can theoretically do that on your own. It's Algebra 2. I hope.
No, I get
You get it, yeah.
Just the plus 2 was random until I saw the plus.
It's because of this plus 1. So what's that limit? 1.
I've never heard of Pascal's triangle.
If you stay after class, I'll tell you how to use it.
It's a gorgeous thing.
It's a gorgeous, awesome thing. If you've seen it, it's pretty cool. Do you guys remember it?
Oh,
I
yeah.
Yeah.
almost derived it myself.
So I'll show you. It's a great trick. It's a trick for multiplying out x plus y to a specific power. It tells you the pattern that happens in these coefficients. Okay, so crap, or I should really say carp. Carp. I won't get in trouble for saying carp, right? Carp. Okay. Carp.
They were adults.
Yeah, whatever. Okay, so what test should you use instead? So we already said that you should use the alternating series test, yep. And so in that case, your B sub n would be equal to 1 over n cubed plus 1. The first thing you check, find the limit as n goes to infinity of Bn. And that limit is pretty obviously 0.
Where does that tell us anything?
No, well, remember for the AST to show you a series converges, the limit has to be 0 and the terms must be decreasing?
We can prove that.
Yeah, we can prove that, exactly. We would next need to show that Bn plus 1 is less than Bn. Well, Bn plus 1 is 1 over n plus 1 squared plus 1, which is, cubed, which is less than 1 over n cubed plus 1, which is Bn. So the series converges by AST. You could actually prove the series converges absolutely by taking the absolute value of the terms and showing that the result converges.
Isn't there a way to use like the remainder or whatever to prove like how accurate you are?
Yeah. We did that. That was on your quiz.
Yes.
Yes. Okay, so stuff that has like things that look like ratios of polynomials is an example of where this test will fail. Okay, so like looking at example 9, if I try to do the AST, if I try to do the ratio test on this one, it's going to also fail. And the idea, sort of hint is that you have some kind of polynomial type thing in the denominator and no other stuff. You need like something to a power or a factorial for the ratio test to give you a result. So what test should you apply to this guy? AST. With your B sub n equal to 1 over 5n plus 1. Is it pretty obvious that this thing is going to converge by that AST?
Yes.
Okay. How about the next test?
Same problem.
Not quite, actually. So when you have number raised to the power, the thing that's happening here is that you proved this ratio test using a geometric series. So you have to retain some geometric elements. And a geometric thing was like something raised to a power, right?
So this one might actually work.
So this one would actually work with the ratio test. As soon as you have something to a power, the ratio test is going to be okay. Why ratio and not root?
Not always the root.
Because the n isn't raised to a power.
I didn't
Yeah.
realize the question.
This is not a p-series. The p-series is when you have a sum 1 over x to the p, n to the p. And officially, p-series are actually positive as well. So because you prove it using the integral test, so you needed positive terms.
Could you take the series of -1 to the n over 5 to the n and multiply it by the series of n?
That would be like assuming distribution works in a way that it does not.
Okay.
Yeah, like it's so no, unfortunately it doesn't work that way. Anyway, if we do the ratio test, n goes to infinity, an plus 1 over an.
Didn't it technically only ask us which test we should use?
Oh, it did. Okay, well,
Wait, was that the root of the ratio test?
ratio is better.
Okay. Why couldn't you use the alternating series test for it?
You could. I think it's going to be harder. If you use the AST, you'll have to prove that n over 5 to the n is decreasing, which would involve a derivative because there's stuff in both the denominator and numerator. But it is theoretically possible, as in the AST would also work. It will get you the same result.
Slower.
So it'll just be slower. If the ratio test works, it's a good one to apply. I am going to skip that because there's one problem that's a little bit different than all the rest. So let's just talk about what tests we would use because I'm not going to be able to finish all of the notes. This will converge, yep. It's actually even going to converge absolutely. And that's actually one thing the ratio test does for you that the AST does not. It tells you that this thing converges absolutely, not just converges. Yes?
On the last one you said that you can't use the ratio test because it was just a simple polynomial. not
Yeah.
raised to the power.
Yeah.
If, that only affects if the denominator's that way? If
It's
the
only, it's if,
numerator is that way?
no, it's if there's nothing else there but polynomials. So if there's only polynomials, either numerator and denominator, but then the ratio test won't work. But once you add in a 5 something to the n power or a factorial, then it will. So it doesn't it wasn't the fact that it was in the denominator, it's just the fact that it's there at all. And that's the only thing there is really the reason. Does that make sense?
Mm-hmm.
Okay. So this guy, what do you think you'd do? The -1 to the n gives you a big hint, doesn't it? What is the hint? No. Alternating series test.
That's not gonna tell us whether it's absolute condition.
No, it won't. So that's what you use to test for convergence. I didn't realize that I actually asked for that. This is my bad. I was just checking for convergence. And if you look at the absolute values, this thing's actually going to diverge. I don't remember how to prove it, though. I think it might be comparison. I didn't mean to do this. The point was, if you try to apply, even though the ratio test tells you both, it still wouldn't work on this guy. So in this case, if you were asked to prove something was absolutely convergent, you have to actually look at its absolute values and see if the series of its absolute values converges, unless the ratio test worked. Okay, and the last one, I'd like to actually, this one, what test would you apply? Root test. That's actually pretty easy. And this last one. So you have a series where its terms are defined recursively. Remember this from the sequence day, kind of like the Fibonacci sequence was a recursive sequence, where the subsequent terms depend on the previous ones, right?
Yeah.
So this formula tells you how to find the next term, and then we're going to take and add up all those things. So like for example, A1 is equal to 2, A2 is equal to 4 times 2 plus 2 over 5 times 2 plus 1 times 2, which is 8, 10 over 11 times 2, or 20 11ths, right?
No.
No?
Oh, wait, yeah, I thought that was.
I think that's
over
right.
2 for some reason.
And that's how you find the a sub 3 by plugging in that number. It's going to get really gross really fast, right? But you want to figure out if the series converges. So what test could we at least try applying? So you're going to be your new favorite test.
Ratio.
Let's try the ratio test. So limit n goes to infinity, an plus 1 over an.
That always sounds bad.
Well, does it really?
Again, like,
Do you know what an plus 1 is equal to? Yeah,
Yes.
what is it? 4n plus 2 over 5n plus 1 times an, right? All that divided by?
And.
Oh, look at that.
Okay,
That wasn't so bad, right?
stupidly easy.
That was stupidly easy. Yes, I do agree. Limit n goes to infinity, 4n plus 2 over 5n plus 1. And that limit is 4/5, right? Which is less than 1. So your sum of an's does what? Converges. I do believe that the way that problem was stated would have confused you, though, had we not done an example. Is that fair to say?
Yes.
Yeah. But once you see the right way to look at it, because of the way the recursive thing works, it depends on the previous term, they end up canceling in your ratio test. It's pretty sweet. So the examples we didn't get to are in the notes online, so you can look at the work, which I think you should be able to understand. If it's not clear, let me know. If they're not there, let me know, because